nattering for the past half an hour. Yeah, welcome to Developer User Group. It's getting really near the end of the year, which is quite strange, but we've survived. So welcome to all, congratulations to all the survivors. And there's just a few announcements that I want to make. One of them is that DevConf is back next year in April. So 5th of April in Cape Town and 7th of April in Johannesburg. And in Johannesburg, I think, or maybe both of them, is going to be a hybrid event. So there'll probably be in person and streaming and everything like that. So however you want to attend, you can. And yeah, you can get tickets now, and you can just apply to speak there if you want as well. So yeah, DevConf is back after being missing for a year. So that's pretty cool. So please join that. And then at the end of the year as well, we've got Geek of the Year in December. We're looking at doing it probably in maybe the first or second week of December. And there's always cool prizes and stuff like that. So get together a team to answer some questions and come join us then as well. Obviously, we still got one more session next month as well of just regular developer user group. But cool stuff. Today we've got something a little bit different. It's not coding, but I think it's still pretty interesting and a lot of engineering. So that seems to tick some kind of fuzzy boxes, I guess, that can be included. And we've got Ryan Kotzen, who's basically, since I've known him, has been making stuff for Kerbal Space Program. So I think he cut his teeth on learning about rockets on Kerbal Space Program, has been making mods and physical hardware to interface with it and all sorts of crazy stuff. I think it was maybe your replacement drug for World of Warcraft.
You got to have one or two obsessions in life, right?
Yeah, so, but I think it's a good obsession. So yeah, a lot of stuff happening with rockets, and I think there's a lot of excitement in that field, and also the potential new stuff that this new generation of rockets and space exploration will be bringing. So I think the whole new industry is only opening up, and obviously they'll all need software. So I think it's a really good thing to understand, and also just for fun. It's good to see massive fireballs in the sky blowing up.
Yeah, there's definitely something primal about it.
Yeah, definitely. It's just fun to watch them go up. Cool stuff. And come down now as well. So that's also great as well. They don't just fall in the ocean anymore. They actually land like proper vehicles.
Yeah.
Okay, cool stuff. So I think Ryan's got a lot to talk about because, yeah, there is just a lot on rockets. So if you've got questions, just type them in the chat and we can go through them periodically. Also, there's prizes for good questions. So Ryan will be using his discretion to give you a prize if he feels like it. if you want a prize, you ask a question. But yeah, if you've got questions, go ahead and ask them on the chat. But I'll hand over to Ryan now and let him go through this fantastic looking presentation. Cool, Ryan.
Awesome. Thanks, Brad. So for those of you who don't know me, I am Ryan Kotzen. I'm a developer at Synatic. And yeah, just started in the startup world again and absolutely loving it. So yeah, if you want to get a hold of me, you can hit me up on Twitter. There's my handle. Also, same for GitHub. Probably the best ways to get a hold of me. Cool. So we're going to be talking about rockets today and some orbital mechanics sprinkled in there to keep everybody interested. So as I'm assuming all of you live on Earth, you've probably noticed we've got some problems. You know, we've got COVID most recently, you know, overcrowding, city politics, that sorts of things. Now we could focus all of our energy on fixing them, or we could just go to Mars. And maybe in the process of going to Mars, we'll come up with some new technologies that'll help fix some of the problems we have on Earth. So before we get too deep into it, in case you didn't already pick it up, I'm not actually a rocket scientist. This is more of a hobby thing. I've tried to be as accurate as possible in all these slides, but I'm not perfect. So if you notice anything that might be wrong, feel free to point it out. Much of my knowledge was, as we spoke about, is from Kerbal Space Program and accidentally killing a few of the green men. Quite a lot more than a few, but we don't really want to go into that too much. Also, the diagrams aren't mine, so I've tried wherever possible to include the original source, and probably each of these slides could be an entire talk on their own. So for this particular talk, what I'd like to just give you is a brief overview of how different pieces of a rocket engine actually fit together. And if you would like to learn more about rockets, I can highly recommend Everyday Astronaut and Scott Manley's channels on YouTube. They have a wealth of really, really good content. So if we're going to go to Mars, we're going to need at least one rocket. And what better way to start within the simplest form of a rocket? So what we've got here is a brief diagram of a bottle rocket, which you might have played with as a kid, which is basically a Coke bottle turned on its head, filled with air, and then filled with water, and then also pressurized air. That's basically what the simplest form of rocket is that you can build. And what will actually happen is when you release the stopper, the pressurized air will force the water out of the bottom, and that generates a thrust. And if that thrust is high enough, what it'll do is it'll send the rocket up. And we've got a quick demonstration on there as to how this looks. So you can see, pumped it up with air, and then it goes like that. But that's not going to help us. That's a little bit too small. Flight duration was very short, and the landing didn't look exactly great. So we're going to have to move on to something that'll actually get us to space. So where is space? So generally what's commonly considered space is the Kármán line, and that's at 100 kilometers above sea level. At that point, air friction is pretty much gotten down to very negligible levels, but it's important to realize that there is still atmospheric particles above that point. It's not like space suddenly stops. And that's why periodically the ISS, which is at about 400 kilometers above sea level, needs to be boosted. Because over time, what happens is it impacts with these small particles and slows down. And so the boosting allows it to stay in a stable orbit. So if we're going to go into space, one of the simplest ways we can do it is to just fly straight up and make sure we have enough fuel to get us above that 100-kilometer point. And that's what Amazon or Blue Origin is doing with their new Shepard rocket. And they'll be opening that up for tourists very soon, if I'm not mistaken. So if you've got the money, you can buy a ticket on a ride, and you'll get to be in space for about 4 minutes, and that'll take you above the Kármán line. You won't get your astronaut wings anymore. NASA recently decided that the requirements to actually get astronaut wings are a little bit more challenging to get, so that not just random tourists will have them. So if we want to get into orbit, that's a little bit more complicated, but infinitely more useful. So how do we get into orbit? Basically, instead of just flying up, we also have to fly sideways. And the velocity that we need to attain in the horizontal vector to do that is 7.85 kilometers per second, which is pretty damn fast. So as you can imagine, that requires quite a bit of fuel to get there. A lot of people think that you need to escape gravity, but at 100 kilometers above sea level, gravity is actually still about 9.5 meters per second. So then the question is, why do we experience weightlessness? The reason that we experience weightlessness is that the spacecraft, as well as the people within the spacecraft, are falling towards Earth and continuously missing it at exactly the same rate. So you feel weightless because of that. And that actually can be reproduced in Earth's atmosphere. This picture itself is from a NASA training airplane called the Vomit Comet, which I think you can use your imagination to figure out why. But the plane basically does a series of S turns and allows for the astronauts to experience what it would be like when they actually get to space. One of the biggest problems with rockets in general is called the tyranny of the rocket equation. There's a calculation that goes along with this. For those of you who are mathematically minded, tried to keep the presentation fairly light on maths, but basically the way you can understand it is, let's say we've got a rocket that's big enough and powerful enough to get 1 kg's worth of payload into orbit. If we now want to get 2 kgs of payload into orbit, we can't simply double the rocket, because what's going to happen is for every pound of fuel that we add onto the rocket to power that into space, we have to bring along more fuel to bring that fuel along into space, or at least to get us closer to space. And so this is a very tricky thing to get right when designing a rocket to cater for a specific payload. And that's, it's been one of the biggest challenges, and that's the primary way that we get around that challenge is through staging. And here we've got a video from Apollo 4. It's a fairly famous video. You've probably seen it before, but it's the separation of the first stage of the rocket and the second stage powering up. And if you look on the right, you can see that first stage is what got the rocket to this point in its journey. It's not actually in orbit yet, and the first stage will now fall back to Earth. Another alternative to staging is called a single staged orbit, or SSTO. There's been a big dream of having a single rocket that could go into space, fulfill its mission, and then come back down and be fully reusable. One of the earliest ones was the Venture Star that was proposed around the time of the space shuttle. At this point in time, no mission has ever been launched to test out an SSO. An interesting concept from the British people is Skylon. That's there on the right. So that's actually a plane that will take off in the atmosphere using normal jet engines and air intakes, and it will then fly up until it gets up into the high atmosphere, and then it'll accelerate really fast along the horizontal plane until it has reached its max in atmosphere speed, at which point it'll close the air intakes and fire off the rockets that will then take it the last little bit into space. So the Sabre engines on that have been tested. As far as I could see, it's still a project that is ongoing, but it is very, very tricky. We also have a question: Bezos versus Branson. Whose rocket is better for going to space, assuming that I can afford it one day? Also, can Branson's plane even be considered a rocket? Is it just a really powerful plane? So good question. Bezos' rocket, for those of you who might not be aware, it's dropped from the side of a modified aeroplane called White Knight, if I'm not mistaken. It is itself completely powered by a rocket engine. I can't remember exactly what fuel it is. I think it's liquid oxygen and kerosene, but I could be wrong on that. So it is definitely a rocket. The Bezos rocket, the new Shepard, that's a rocket all the way from the ground to the common line. Which one would you prefer to go into space? If it was me, I'd take the new Shepard, because you get to experience the parachute as well as the rocket launch from the ground. With Branson's approach, you kind of have to fly around like a normal plane for a bit, and you have to get to your target and then launch from there. Cool. Yeah, so I think the reason Musk isn't on that list is because everybody would pick it. Cool. So as you can see, Branson's approach is fairly similar to the Skylon. It just doesn't have to take the whole carrier plane into orbit. Okay. So if we would like to get up to those orbital velocities and into space, we're going to need a few things. Firstly, more power. We're going to go through that first. And then the ability to maneuver, because we don't want to go just straight up, as we've spoken about. We want to go sideways. And then, of course, there's a whole bunch of other things like Space Netflix that we won't consider for this particular talk. So it's the time for the controlled explosion. As we saw, a bottle rocket isn't going to get us to space. We need some sort of exothermic reaction. That's a reaction where it puts out more energy than it starts off with. And one of the things I always talk about in rockets is beware of rapid, unscheduled disassembly, aka explosions. So the first and most simplest form of rocket that would be able to get us up to the sort of velocities we need is a solid rocket. It's considered to be simpler than liquid engines. Basically, what happens is we take a fuel and an oxidizer, we mix them together in solid form, and it's generally combined with a binding agent, kind of like eggs if you're making a cake. And then that mixture is poured into a mold. And depending on the shape of the mold, we can actually throttle the rocket at different points along its flight. I've included some screenshots there of how the different shapes look for different types of thrust profiles. This is also a lot safer to store. So with a liquid-fueled rocket, generally we'll use cryogenic fuels. These are fuels that are cooled down really, really cold. And the reason they do that is to increase the density. So as you know, hydrogen is the lightest element. And so when we want to store it, if we were to use a tank to store it at 1 atmosphere of pressure, the tank would be ginormous and the whole tank would weigh way too much. So we actually cool it down so it'll fit into a smaller tank. And that also gives us more thrust. Problems with the solid rocket booster is it can't be shut down once you've started. So if you have to abort, basically it makes things a little bit trickier. It can't be throttled in real time if needed, but as I mentioned, it can be throttled generally beforehand. We've also got a question about a nuclear-powered rocket. I do talk about that in a little bit, so we will get to that. We're really going to focus on standard chemical rockets, though. Liquid rocket engines. So these are one of the most common because the technology behind them, even though it's more complicated, the advantages of it over solid rockets are quite a lot better. So as I mentioned, we use cryogenic propellant on average. And then we have 2 categories of reactions that can occur. We either have combustion, which is when something burns in the presence of an oxidizer. So there'll be a fuel and an oxidizer, or we have what's called a hypergolic fuel. So these are 2 chemicals that when mixed together cause a reaction. So if you can think back to high school doing science experiments, your teacher probably put potassium or lithium in some water and it spontaneously reacted. That's pretty much what happens. And I'll take you through some of the hypergolic fuels in a little bit. But we have the different components of a liquid fuel rocket engine. And this is going to be where a big chunk of the talk actually is. So we've got our propellants, generally stored in a cryogenic tank. Then there's all sorts of pipes and plumbing to get the liquid fuel from the tanks into the combustion chamber where we can have our reaction. We have an igniter that will actually set the reaction off, because if you don't have an igniter and you just mix liquid fuel and liquid oxygen together, you're just going to have SAD and you're not going to go to space today. Then we have fuel injectors, which inject the fuel and oxidizer into the combustion chamber in an optimal way. We have the throat of the combustion chamber. That's where the hot gases will exit. And then the nozzle, which carries on from the throat to the atmosphere, where it'll actually get expelled as exhaust. We're going to go over each of the different components in the liquid fuel engine. But before we do, I just wanted to show you that there is another type of engine called a hybrid engine. This has a liquid oxidizer and a solid fuel grain. What basically happens is you start the liquid oxidizer flowing into the chamber of the rocket, the hollow chamber between the solid fuel, and you start the reaction by triggering the igniter. And then if you need to throttle down, you simply control, well, I say simply, but nothing in rocket science is ever simple, but the principle is fairly simple. You throttle the amount of oxidizer that's actually going in, and you can control the reaction that way, and you could cut off the oxidizer completely if you wanted to shut the engine off. Before we get too much into the details of the components of a rocket, there are a few things that we need to understand that are important when considering how to build a rocket. So the first thing is the weight. Obviously, the heavier, all other variables being the same, the heavier your engine is, the worse off your rocket engine is actually going to be. So we want these things as light as possible, but still not flimsy so that they'll explode or melt. Then we have the net thrust. The net thrust is basically the weight of the engine minus the thrust, and it's actually a little bit more complicated than that. There is the whole calculation on Wikipedia to calculate the net thrust because it does change with atmospheric pressure. Then we have specific impulse, which is how we measure an engine's efficiency. The calculation for this is also fairly involved and has a whole bunch of different variables, but it's the impulse per unit of propellant. So the propellant designed for that specific engine. Impulse is the integral of the force over time. So if you're a math geek, you can totally go check that out. It's generally measured in seconds, and that's for 1 unit of fuel, how long will it burn for? 100 units of fuel, how long will it burn for? And then important to note about ISP or specific impulse is that a engine generally has 2 of those values, one for at sea level and one for in a vacuum. And then at any particular altitude, you can use that to calculate how efficient it would be. Then we have the standard thrust weight ratio, the cost of the engine, the failure rate of the engine, availability of the engine, and construction time. So for the Raptor engine that SpaceX is using, you can see they're pumping these things out of the factory because they need a whole bunch of them for Starship. And they keep blowing up their test vehicles, which is part of the iterative design process, as us developers actually know. We also have a comment there. The plumbing on the Super Heavy is hypnotic. Yeah, it's really quite a thing of beauty to see. So I'm just throwing up a quick overview of the liquid engine before we dive into the pieces, just to keep this in your mind as we go through it. We're going to touch on each of them. First up, we have the propellants, and we're going to start with the simplest. Simplest are called monopropellants. This means there's no oxidizer, there's just the fuel. And this fuel is passed over a catalyst, which causes the reaction to occur. One of the most common is hydrazine and aluminum oxide, which is coated in iridium. And we also have hydrogen peroxide plus a silver catalyst. So these are engines that are not very efficient, but because they are quite simple, we can use them quite a lot for maneuvering. So a lot of spaceships use that to actually maneuver when they're in space, because you can have multiple of them positioned around the ship. Then we have bipropellants. These are by far the most common of them. So this is where we have a fuel and an oxidizer, or 2 different hypergolic chemicals that will mix together. The liquid propellants generally have a higher efficiency than solid rocket propellants. As we spoke about, hypergolic fuels, they have that spontaneous ignition when they're mixed. And the most famous version of a ship that uses was the Apollo lunar lander. And this is because they needed it to be relightable. So you can, tap the thrust as and when you need it. You don't want to run out of igniters when you are trying to land on the moon. Then we have liquid oxygen and a fuel. We have quite a few ranges of fuel. Important to note, different fuels have different characteristics, like how available they are to manufacture. They have different efficiencies, different burn rates. So an engine, you can't just switch out the fuel like in your car. You can't switch to diesel. An engine's built for a specific fuel. So hydrogen is incredibly common because it's very efficient. Methane is what's being used on the Raptor engine, and that's because methane can actually be manufactured on Mars through a decomposition process with the atmosphere and some of the elements that are found in the soil. We have some natural gas rockets. We have kerosene. Kerosene has a very high thrust, so it was used a lot. For example, the Apollo Stage 1 that used kerosene. The first liquid rocket used alcohol. It's not common in industrial, in modern rockets. You can even use gasoline, and there's also carbon monoxide, which can be burnt, and when it's burnt, it produces carbon dioxide. And this is planned to be used on a Mars hopper robot that will actually use the carbon monoxide. Then we have an exotic form. It's never been flown before. We have tri-propellants. So there's two types. So the simplest you can think of is we might have a liquid oxygen tank and a kerosene tank, and then a liquid hydrogen tank. And when we're low down on the atmosphere, we'll burn the kerosene in our engine, and the engine will be designed to cater for both types of fuel. And then once all the kerosene is gone and we're higher up in the atmosphere, we'll switch our tank to using liquid hydrogen. This has promising consequences for a single staged orbit rocket, because then you won't have to have two different sets of engines to burn two different types of fuels. You can reuse the same engine. Then we have another type of tri-propellant, which is a simultaneous burn. This is where we use generally an oxidizer and a fuel, and then some sort of exotic high energy metal to boost the performance of our fuel. So we might have oxygen and liquid hydrogen plus lithium. We got a comment over here. Back in the 50s and 60s, when they were first figuring this all out, how were they able to calculate the efficiency levels in space? Was it just trial and error with each new rocket that they sent up? So good question. I don't really know. I can imagine that for a particular fuel, you know that its weight. So let's say you have a set tank volume, you'll know how much fuel you can actually compress into that. And then you know that for a given fuel, how much thrust you can actually generate with it at sea level. And then, yeah, I guess just trial and error to see how much you can get with it at above altitude, at different altitudes. Yeah. Okay, try with that. Then we have pumps. So these are a lot more complicated than I originally thought. The whole idea about how to get the fuel from the tanks into the combustion engine on the surface of it seems fairly simple. But as with pretty much everything in rocketry, as soon as you dig down into it, you see that there's been a ton of science and thought and complexity that actually goes into it. So relatively new, but fairly simple is the electric pump. So this, you would just basically have a bunch of batteries on your rocket and a DC motor that would then pump the fluid directly from the tanks and into the combustion chamber via the injectors. The problem with this is batteries are very heavy. And as we know from the tyranny of the rocket equation, we want to try and keep weight down as much as possible. So a lot, pretty much, there's a startup rocket company that's using them, but other than them, nobody that I know of is actually using electric pumps. Then we have turbo pumps. Basically, what happens is these have a turbine that's turned by a gas that basically the exhaust gas, or its small rocket engine of its own that will heat this gas and cause it to turn the pump, which along the same crankshaft will then turn the impeller, which will cause the fluid to move. The problem with that is you've got a very hot gas and a cryogenically cooled fuel or oxidizer propellant right next to each other. So there's quite a bit of heat exchange along there. So it is very, very tricky. But this is critical to get right. The pumps are responsible for throttling the engine and ensuring that they're not starved of fuel or oxidizer. And if you have too much fuel or oxidizer, you're going to have a rapid unscheduled disassembly, which is exactly not what you want. If we look at the pumps and how the different types work, I've got this diagram over here, which I have borrowed from Everyday Astronaut because he illustrated it very well. You can imagine a progression from left to right-hand side as engineering got more complicated and we got more advanced ways of building rockets. So at the very simple step, what you have is a fuel and an oxidizer tank, and they're going to then have their pipes set up so that a small amount of the fuel and the oxidizer gets sent to a gas generator, which is basically its own combustion engine. So the fuel and the oxidizer will burn in there with an igniter, and that will cause the pump to work because that gas will then get pumped over the turbine, which will then, along the same crankshaft there, you can see it will then turn this turbo and that turbo pump. And then the exhaust gas from that will be pumped directly outside. As you can imagine, with this particular setup, you don't get all of that thrust that could have been used in this exhaust is now wasted. Then we move on to the closed cycle. So the idea with this is instead of just dumping that exhaust gas overboard, we'll send either more fuel or more oxidizer into the gas turbine, and then the exhaust will contain some fuel or oxidizer, and we'll just pump that into the combustion chamber. Now, the problem with doing a fuel-rich closed cycle engine is that that exhaust gas is full of soot. So it'll actually clog up the combustion chamber and cause your injectors to not work very well. So what most rocket engines side with doing is they use an oxidizer-rich closed cycle. And they pump that directly in. Then moving on from that, and this adds quite a bit more efficiency. And then slightly more efficient than that is the dual shaft fuel-rich mix. Basically, what will happen here is that the turbo pumps are pumped with more fuel than oxidizer, and it's symmetrical on, well, not symmetrical, but they'll get the fuel flow will be symmetrical. The turbo pumps will then have just enough oxidizer to get the reaction going. The majority of the oxidizer will go straight into the combustion chamber, and the exhaust from both of those will then be piped into the combustion chamber. Then we have the full flow stage combustion engine. So to date, there's been 3 types of engines that have been built that are full flow stage combustion. This is the pinnacle at the moment of engine technology, and the Raptor engine that SpaceX is using on Starship, which has been tested and which has flown Starship a little bit already, utilizes this. So what happens with this is all the fuel and all the oxidizer is pumped into the turbo pumps. One side is fuel rich, the other side is oxidizer rich, and that results in an oxidizer rich exhaust and a fuel rich exhaust, which then get pumped into the combustion chamber. And this allows for the most efficiency for the same amount of fuel. Then we have 2 slightly less well-used engine cycles. One is the tap-off cycle. Basically, instead of pumping fuel or oxidizer into a gas generator, what they do is they pump them directly into the combustion chamber, ignite them, and use some of the exhaust gas from that reaction to power the turbine. And then the expander cycle, which basically runs that cryogenically cooled liquid fuel around the bell of the engine, so that it heats up, expands, and turns into a gas, which they then pump through the turbine and then back down into the combustion chamber to be burnt. This keeps the engine bell cool, which prevents it from firing. But as you can imagine, the power in the turbo pump is limited by how hot the engine nozzle actually gets. And with all of these, a very tricky thing is how to get the turbine started. Because if you need fuel flowing into the gas generator to power the turbine, but you need to power the turbine to get the fuel flowing, it's a bit of a chicken and an egg solution. And it's a bit outside of the scope of this to actually cover how they do that. Can't jet turbines be used in low atmosphere? So jet turbines, yes, they can, but then you would have to dump them overboard to save weight. So it's simpler generally just to stage them. The Sabre SSTO engine that I was talking about earlier is actually a jet turbine that has the ability to close its air intakes and burn oxidizer and jet fuel at the same time. So that's a similar way to do that. As you can imagine, this is a rocket engine, so I've oversimplified things a hell of a lot. There's tons and tons of piping and tubing and wires and coolers and all sorts of things that are not included in here. A lot of the time, you know, you need helium for back pressuring the tanks so that they keep flowing. And the turbine itself sometimes needs to be cooled. So if you are interested, check out the Everyday Astronaut talk on fuel pumps. Then we get on to injectors, which, as with a lot of things, seems simple on the surface of it, but then you start digging in and there's tons and tons of complexity. So the simplest way to think about it is that it's a shower head. So the fuel comes in, it gets spread out, and it showers down. The things that we're trying to aim for with an injector is atomization of the propellants. So we want them to be as small as possible, tiny droplets. We want them to be mixed as best as possible with the opposing propellant, so the fuel mixed with the oxidizer. We want to make sure that there's as little unburnt propellant as possible, and we want to control the flow, because if we allow too much fuel and oxidizer into the combustion chamber at once, what will happen is the engine will explode, and that's not good. And if we have too little, we're not going to produce enough thrust. And we want to minimize the heating of the engine bell itself. So what some of the fuel injectors will actually do is they'll spray the liquid fuel around the sides of the bell to help cool it down. So some of the common injectors that are used on the bottom of the screen, we've got the ones that we used sort of in the Apollo era, basically a pipe and a directed nozzle, so that the oxidizer will spray up and then the fuel will spray up and they will intersect or impinge at a specific point. And there's different ways of actually doing this to form a cloud of atomized fuel and oxidizer particles. Then in the top left, we've got a swirl injector. These are fairly common now. What happens is they are built in such a way that they induce a swirling motion in the liquid oxidizer as it's forced through the injector, and then the fuel itself just passes straight out. But because the oxidizer is swirling, as it exits the injector, it expands and it comes into contact with the fuel. We then have a pintle injector, which is basically the oxidizer flows out directly, the fuel flows out, and it bumps into a little pintle, and that causes it to spread outwards. And so it immediately then comes into contact with the oxidizer. And then we have what's become more common now is the unlike quadlet injector. So that's basically just a hole, 4 holes at an angle with an intersection point. So 2 streams of oxidizer plus 2 streams of fuel will hit and intersect and then expand from there. Then we come to the combustion chamber itself. If you've ever done anything with a pressure cooker and been scared for your life, you can imagine that's kind of what a combustion chamber has to do, but on steroids. This is where the fuel and the oxidizer actually mix and they react. So the engine combustion chamber itself has to be very well built to handle those high temperatures and pressures. Very important is that the pressure in the chamber must be less than the pressure that the turbo pumps or the pressurized tanks are generating. Otherwise, the fuel and oxidizer mix isn't going to actually flow into the chamber where the reaction can happen. Then what we've got is the igniter. So as we said, without hypergolic fuels, we need some sort of ignition source. So funny enough, these are often little pyrotechnic charges or explosives that'll get the reaction started. With liquid, with an oxidizer and a fuel, once the reaction started, generally the reaction will be self-sustaining as long as you don't cut the fuel or the oxidizer off. But what's interesting enough is actually the combustion chamber tends to retain its heat. So even if you were to switch it off for a few seconds, you wouldn't need a new ignition source if you were then to inject the fuel and oxidizer in within that few seconds window. Hypergolics, they can be used to actually start the reaction. So some engines have a small amount of hypergolic fuel that they send into the combustion chamber along with the liquid oxygen and the oxidizer and the fuel, and that'll get the reaction going. And then there's a pyrophoric agent that can also be used. That's generally only used to get the engine ignited when it's still on the pad. So that's something that when it comes into contact with air, it will ignite. Solid rockets, they generally use pyrotechnics. And yeah, some engines are designed like the SpaceX's Falcon 9, the Merlin 1D engine, that's designed to be relit numerous times so it can perform the deorbit burn and the landing burn as well as the initial launch burn. So obviously the engine has to be built to cater for multiple ignitions. And that's generally done with multiple pyrotechnic charges. Then we come to the nozzle. This is the traditional bell shape that you've seen. Very important to note, only half of an engine's thrust actually is coming from that combustion chamber. The other half of that thrust is coming from that exhaust gas pressing against the nozzle. So the nozzle is critically important in getting enough thrust and enough efficiency. And the de Laval shape of nozzle is one of the most common, and it's used in pretty much every single rocket, and it's defined by his equation. A nozzle needs to be designed for a specific atmospheric pressure. So here you can see the Merlin, which is used on the Falcon 9. On the left hand, it's the exact same engine. The only thing that's different is the bell or nozzle that they use. The one that's for in atmosphere has a much smaller bell, and the one for the vacuum engine has a much larger bell. So technically, the most optimized bell for in a vacuum would be infinitely long. Now, because we don't have an infinite amount of material, and that even if we did have that infinite amount of material to build one, it would be very heavy. And by the time you built it, you'd be already on the other side of the universe. So there's an equation that they use to calculate at what point does the weight of the bell outweigh the efficiency gained by having the engine bell extend further down. Then on the right-hand side of your screen, we've got the different profiles of an engine at different atmospheres. So an underexpanded nozzle results in an overexpanded exhaust. As you can see, that's the first one. That's just inefficient, and sometimes you have to deal with that because to the best of my knowledge, there's no nozzle that actually changes shape as you go through different atmospheres. But that would be pretty cool if you could build it. Then we have ambient. This is when the exhaust gas is exactly matching the atmospheric pressure, and that's the most efficient. Then we have underexpanded. You can see that the exhaust flame or exhaust gases are starting to peel away from the nozzle, and that's also inefficient. And then if you have grossly overexpanded, you'll see that the exhaust gas is coming away from the nozzle well before the edge, and that's actually very dangerous, and that can cause all sorts of oscillations which will tear the engine apart. And in addition to that, the other thing that they can do is they can cause the forces to be at weird angles, so it'll actually send the rocket off course. So you don't want that. One of the big alternatives to a bell-shaped is an Aerospike engine. So instead of sending the gas out the bell, what they do is they angle the exhaust vents so that they push against a plate. And this can either be a toroidal, that's a sort of toroid, which is kind of like a circle, for those of you who might not know your geometry very well, kind of like a donut, or a linear engine, which is a bell that's been inverted and expanded along the lateral axis. And these engines are really efficient for different atmospheres. Test engines like this have been built, but none have ever actually been flown. And the reason for this is generally with a linear Aerospike, cooling becomes a very, very big problem, because now you've got two exhausts pointed at the same point, and you can't cool it as easily because you can't pump the liquid fuel around the same surface area as you can with a standard bell. And then we've got the gas exchange version of how that worked on the linear Aerospike, which they were going to use on the Venture Star SSTO. So the exhaust gets pumped over there, and then the fuel and oxidizer get pumped to the dual combustion chambers over that way. Somebody mentioned nuclear rockets earlier on. I'm not going to touch on them too much because this presentation is already quite long. But basically, this is with a fission reaction. We're not going to talk about fusion reactions because we can't even keep those stable on planet Earth. So probably not a good idea to try and power our rocket with it. But a fusion nuclear rocket engine basically works instead of combustion. The propellant is pumped into the reaction chamber of the nuclear rocket itself, and that causes the propellant to heat up. Generally, I think if I'm not mistaken, a nuclear rocket should have double the efficiency of liquid oxygen and liquid hydrogen. The problem with this, obviously, is you don't want to use them in atmosphere. They won't generate enough thrust in atmosphere, and you would be spreading radioactive material within the atmosphere. But space is full of radiation, so these are generally a good idea if you're going to go on a long journey, say to Mars, that's going to be months, and you want to maximize your engine efficiency by using as little propellant as possible. You don't need liquid you don't need two propellants in here. You'll only need one. And then we have the electrical propellants. So these are generally Hall thrusters and that sort of thing. What they do is they ionize a noble gas. Generally, xenon is the most popular one that's used at the moment. And they basically take electrons away from the xenon atoms, and they accelerate them either through an ionized or magnetic field. And just before they exit the rocket, they put the electrons back on the particle so that it'll have it won't build up that ionization. And that these engines are actually in use now, unlike their nuclear counterparts, which, if I'm not mistaken, haven't been used yet. And they are generally used either for station keeping, so to keep a satellite in the right place, and also for interplanetary probes. I think New Dawn used a electrical engine to do that. You can get incredibly high efficiencies with these engines, which is primarily why they're used. The problem with them is that they don't generate very much thrust. So they're ideal for use on things like CubeSats, which are low mass. And if you want to go do deep space exploring with your CubeSat. Then we have a very interesting one, still with the fission idea. This was sort of proposed, as you can tell from the diagram, from the Apollo era. This is the Orion spacecraft. So what it has at the back is a pusher plate and a little depositor. So the theory with this was, if you were to take small nuclear weapons, you could send them out the bum of the spacecraft and detonate them just behind the spacecraft. And the shock wave would push against that pusher plate, and that would send the spacecraft forward. And you could have, hundreds and thousands of these nuclear weapons that you could just eject out the back and detonate to accelerate your spacecraft, which is pretty heavy metal, if I have to be honest. It's like quite an interesting way of propelling a spacecraft. As you can imagine, this was never built, and it's quite a large spaceship, so it would have to be assembled in orbit unless you wanted to set off a series of nuclear weapons in atmosphere, which probably wouldn't be good. Cool. Then we come to the concept of delta V, or change in velocity. So if, for example, we are in orbit around the Earth, and we have a certain mass, we need a certain amount of delta V, or change in velocity, to get from orbit of the Earth to Mars or the Moon or wherever we might be going, or just to perform an in-orbit maneuver. And for interplanetary transfers, these are normally plotted out on this diagram on the right here, which is called a pork chop. So you'll see there's these blue lines, and at the center of the blue line over here, you'll see there is the most efficient time to lead to depart. So you have launch date on the x-axis and arrival date on the y-axis. So if we are within that circle, we're doing the most efficient transit. And along the red line, you'll see the duration. So you'll see that oftentimes what happens is the more efficient the particular profile is, the longer it takes to get there. Very important if you're going to be doing manned missions. Not as important if you're going to be launching a probe, but if you need to time it up with certain celestial events, this becomes quite important. And there's even a mod for Kerbal Space Program that will do these pork chop diagrams for you if you want to go to Duna or wherever else you in the Sol system that you'd like to go. Cool. So now we've spoken about how rocket engines actually work. We need to talk about how to maneuver, because as we spoke about, we don't want to just go straight up. Although technically, if you do have enough delta V, you can go straight up until you reach escape velocity from your planet, at which point you won't have to worry about just coming straight back down. But that's not the most efficient way to actually launch a rocket mission. So when we're in atmosphere, we can use rocket fins. So these work just like airplane wings. They have actuators. They sometimes have actuators. Sometimes they're just there to stabilize the rocket. The problem with these is they add weight. So if you were to use them on a particular rocket, you want to ditch them in an early stage as quick as possible. They do not work in space. No amount of wing in space will allow you to navigate, to maneuver your plane. Then we have thrust vectoring. This is basically where either the whole engine itself is able to gimbal, or just the nozzle is able to gimbal, so that we can actually move that thrust around in order to orientate our vehicle. You'll also see that on fighter planes like the F-22. They're able to vector their thrust to perform like really crazy maneuvers in a dogfight, which are pretty cool. And then we have Varina engines, or cold and hot gas thrusters. So these are basically scaled down little rocket engines that allow us to orientate our spacecraft. Of course, they do add weight, and depending on how complex they are, they might add a lot of complexity with the plumbing, as we saw. However, these are very critical for precise maneuvering like docking. All right, then in terms of orientating, some important concepts to know. We've got pitch, roll, and yaw. We've got movement along the longitudinal, vertical, and lateral axis. So if you just keep this in mind when you're flying in Kerbal Space Program, you can make sure that you use the correct terminology. Then we have fins. I wanted to show you a demo of how these look. And of course, I tested it so that it would auto start, but then it didn't auto start. So now I click on it. So here we've got a little model rocket in a wind tunnel, and it's got some fins, and you're going to see he's going to hit it with his stick. And no matter how well he hits it, it's fairly stable. And that black point is the center of mass. It's basically a weight. So the point at which the center of mass and the fin is are very critical in ensuring stability of the rocket. Cool. Then we have an example of thrust vectoring. Be thankful that you can't hear this because the sound is really loud. So I'm just going to get deafened and turn that off. So this is at, I think it's NASA's space test there, rocket test engine facility. You can see the engine itself is gimbaling or moving around, and that allows you to control the direction of the rocket. And instead of having wings, having those actuators, funnily enough, does allow you to save weight and maneuver the rocket around. Then we come to cold gas thrusters. So these were used on the manned maneuvering units that the astronauts used on the space shuttle. They had about 25 meters per second of delta V, which is not a hell of a lot, but because you're not doing interplanetary transfers in your spacesuit, it was enough to get around, maneuver to the Hubble, that sort of thing. The 24 different thrusters placed alongside at different points along the unit itself. The astronaut was able to control all 6 degrees of freedom with his left and right hand, and it even had an automatic hold function. So once he got into position, he could just engage that, or she could just engage that and have the thing sit where it needed to be while he or she did their work. Then we've got hot gas thrusters. This video shows a Soyuz spacecraft that's coming into dock with the ISS, and you can see the little plumes of exhaust gas being sent into space. So this is the Russians very fond of their monopropellant and hypergolic fuels, using unsymmetrical dimethylhydrazine and nitrogen tetroxide to navigate there. We got a question. How big are amateur rockets that we see launched at Death Valley and such? They do, like model rocket enthusiasts, get really detailed. They'll build their own injectors and that sort of thing. They can get quite a lot bigger than you would think. I think it's like 4 or 5 meters. If I don't have the stats offhand, but they're pretty big. Cool. Let's go to the next one. We missed a slide. We missed a few slides. Okay. Then we come to some orbital mechanics. So, and here we have an example from Kerbal Space Program of an orbit. So the center of our orbit is centered on planet Kerbin. You can pretend it's Earth if you don't play Kerbal Space Program. We have our periapsis, which is the lowest point in our orbit, or the closest point to the planet we're orbiting. And we have our apoapsis, which is the furthest point from our planet. On Earth, these 2 points have a specific name. It's apogee, like the computer game development house of yore that was very popular when I was a kid. And then we've got the perigee, that's specific to Earth. So around every other orbital body, we refer to them as the apoapsis and the periapsis. And you can see that this is an elliptical orbit. But we also get circular orbits, which where the periapsis and the apoapsis is pretty much everywhere. And then we have parabolic orbits. So that's where you are escaping from the particular planet that you're orbiting around. So they form a parabola, and an orbit has inclination, so that's along the horizontal plane. And an orbit can be prograde, so with the rotation of the planet, or retrograde, against the rotation of the planet. We try and keep most orbits prograde because we actually are able to save some delta V in our launch by doing that, because the spin of Earth actually allows that rocket to get a little bit further, a little bit more bang for a buck. Then again, stolen shamelessly from Kerbal Space Program, different ways that we can change our orbit. So we've got the prograde direction, that's in the direction that we are traveling in. We've got retrograde, so that's opposite to the direction we're traveling in. We have the normal, which is, as you can see on there, it's the up and then the anti-normal, then radial in, that's towards the body, and radial out, that's against the body. So when a prograde burn or a retrograde burn is generally used once we're in orbit. If you would like to deorbit, you have to burn retrograde. That's the most efficient way. So you lower your periapsis until it interacts with the atmosphere. And we can then also use our prograde burn to do a translunar injection or a trans-Martian injection. So an interesting thing with the Oberth effect is if you're going to travel to a different body, you always want to do your prograde burn at your periapsis, at the lowest point, closest to the planet. And that's because that's the point at where you are going the fastest. And by doing it that way, you actually get more fuel efficiency. If you are interested in how that math works, go check out the Oberth effect. I'm not going to explain it because it's going to take forever. Then the most popular way to get to a different body is by a Hohmann transfer. That's where you burn prograde at the exact right time. And you can see here a diagram when Earth is there and Mars is there. They aren't at their closest points. They are at their closest point, and that's where you want to launch so that you intersect with their orbit. We got a great question. I think this one's worth the prize, about Lagrange points. So this talks about n-body physics and how gravitational fields interact. So that's a Lagrange point between Earth and, for example, the moon. There are, if I'm not mistaken, 4L points, Lagrange points. These are the points at which the fields of gravity are balanced. So if you wanted to have a communication satellite between Earth and the moon, then you would put it at a Lagrange point so that you don't have to use fuel to do any station keeping, and it'll never go behind one of the two planetary bodies. Very interesting point to look out for. We spoke about deorbiting. So a lot of people would say, if you're in space and you want to get back down to the planet, point down towards the planet and burn your engine. That's not actually how you do it. You point opposite to the direction you're traveling, fire your engine until your orbit intersects with the atmosphere. And you can actually use that to slow your orbit down and then get back into orbit. So that's called an air braking maneuver. And a lot of space probes use this when they are coming into the Martian orbit to slow down without having to use fuel. They dip into the atmosphere of Mars. Then you can do an inclination change. So this is where you are at a certain angle, your orbit's at a certain angle, and you want to increase it. So let's say you want to go into a polar orbit and you're in a slightly inclined orbit. Funny thing with orbital mechanics, which is, I always find orbital mechanics is counterintuitive. It's cheaper to raise your apoapsis and then do the plane change at your slowest point. So apoapsis, the furthest point away from the planet, is where your velocity will be the slowest. Now, if you can think about a car, if a car is traveling at 200 kilometers an hour and you suddenly want to change direction, that's very tricky to do. Whereas if the car is traveling 10 kilometers an hour, you can change quite easily. So that's where this inclination change comes. So it's often cheaper to raise your orbit, do the plane change, and then lower your orbit back down than it is to just start doing the burn for the inclination change. Just going a bit fast because we're running out of time. You can also do a radial orbit change. So you can see here, it looks like it swings the orbit closer to the planet on one side and further away from it on the other side. Then we have rendezvous, which is another fairly counterintuitive thing. So if you have two spacecraft that are in the same orbit, but they're nowhere near each other, if you are the one that's further ahead in the orbit and you need to slow down to catch it, what you actually have to do is you have to speed up to go into a wider orbit, which is a slower orbit, so that you can let the other ship catch up to you, which is, again, quite counterintuitive. But if you've ever played Kerbal Space Program and tried to rescue your Kerbals in orbit by docking with a stranded spaceship that ran out of fuel, you'll probably have spent a couple hours trying to get this right. And it's quite interesting. Thanks, everybody. That is my talk on rocket engines. I know I went through it quite fast and it's quite a complex topic, but hopefully we've got a few more questions and we can dive into some of the deeper mysteries of space, and maybe I can try and answer them. My pleasure, Andre.
Cool. Thanks, Ryan. Thanks for that. That was fantastic. It was like every part of a space system I think you talked about there. Next step is building a space colony, I guess, with this knowledge.
Yeah, I think
Cool.
we must get the ZA dev community. We'll build a model rocket, go launch it in the Karoo, and do a bit of a Burning Man while we're there.
Yeah, why not? Why not? Cool. So yeah, like Ryan said, if you got any more questions, we can go through them. I think Ryan's still got some things he can show you, but we just kind of called it an hour because I know some people have got like kids and dinner and other things to do. But for those who want to stay, you're welcome to stay and ask questions for a little bit, and Ryan will go through as much as he can, I think, before he gets bored. Okay, cool. So yeah, fire away with questions, I think. Well, I'll start with one. With Starship, how many launches do you think before they get it to orbit and back successfully?
So they've done a lot of Yeah, they've done a lot of iterative testing on their main booster. So I would say that the main booster will probably from now, I'm gonna put money on it. I say 3 to 5 launches.
That's
When they're
not a lot
actually
when you think about it.
yeah, when they're actually targeting it. I'd love to see it get to orbit on their first attempt. That'd be freaking amazing, and it would be a testament to how iterative design can actually work in these archaic, highly regulated industries. But I don't know. I don't think I'm brave enough to put money on the first launch. So I think we'll see it by launch 3.
Yeah. Sure. Yeah, that's aggressive, eh? Sure.
Yeah.
You would think that it would be like, like years or decades long for other rocket programs to even try to lift
What
off the
would make
first
me
time.
very happy is if Starship gets to orbit before the SLS system. I think that'll prove just how corrupt the American way of building rockets on a government budget actually is, and hopefully that'll force them to scrap the project and reassign those resources to actually valuable space exploration rather than trying to have what amounts to a genital measuring contest.
Okay, cool. We got a question from Megan. Said one movie referred to a slingshot maneuver around a planet. Can you elaborate on that a little bit? I
Yeah,
remember the
that's
slingshot
a
from Apollo 13 around the moon, trying to get
yes,
back
and they
when
also
they
did
were
it
stranded.
in Armageddon. So this will do. So imagine that you are some background on the slingshot maneuvers. These were utilized quite heavily in the Voyager series of spacecraft. So these were probes that were sent out into deep space. They're the furthest and fastest man-made objects ever created. So what basically happens in a slingshot maneuver is a probe or a spacecraft is coming in towards a planet. It's not in orbit around the planet. It's passing by it. And so if you angle it right, a planet that's let's say it's spinning clockwise, if you angle it so that your trajectory comes on the side of the spin that is not clockwise, so I mean that is going with the clockwise, what will happen is the planet will slow down by a fraction of a percent, like a tiny amount, but the spacecraft will speed up by a noticeable percent because the mass difference between the spacecraft and the planet is incredibly vast. So the bigger the planet, the more mass you can actually steal from the planet. From its not the more mass you can steal from it, but the more velocity you can actually steal from that planet. So you can imagine a small, tiny probe slingshotting past Jupiter can pick up a ton of momentum. Equally, you can do a slingshot so that you're going against the rotation of the planet, and that'll actually slow you down. So if you wanted to come into orbit around Jupiter, you would plan your slingshot to do that, so that you can actually get into orbit around Jupiter. And that's precisely what the probes do that explore the Jovian system, is they plan those slingshots to time it so that the trajectory comes alongside against the spin of the planet, and that slows it down so you don't have to expend as much fuel to get into your desired orbit. Cool. Got any other questions?
Let's look for more questions there. Anything else?
This is a great question from Robert. I think this is worth another prize because it was this Rob who's part of the organizers or a different Rob?
That's Robert, part of the organizers. He can't get a prize.
Can't get a prize.
Who else got a prize, by the way?
It was the person who asked the question that I liked about Lagrange, MG Ferreira. Question about Lagrange points. Okay, what sci-fi
MG,
is
well
the
done
best?
Again.
Yeah.
MG says
Okay.
he's already got a prize.
Okay, I'm
so he
delegating
can-
responsibility to him to pick somebody else.
There we go. Well
Okay,
done.
so the sci-fi show with the best orbital mechanics is The Expanse, in my opinion. So they have a type of engine that is unlike what we have today, but they still are very accurate in how the orbital mechanics and the timings and that sort of thing actually work. So the type of engine they have burns constantly, unlike our engines. If we try to burn our engine constantly, we run out of fuel. But because they've got, I think it was fusion engines or reactors, they can actually constantly burn fuel. Now, what actually happens there is, it's very interesting because you're no longer trying to match orbits with something. You're burning in the direction of the thing you want to go to. You burn for halfway to speed up the whole time. And then you do a flip and burn maneuver, which is where you then start slowing down for the other half of the journey, which is quite interesting. And I think the show that had the worst orbital mechanics, probably Star Wars. Everything's just like kind of is constantly flying around, or maybe Armageddon. When they're on the asteroid, sometimes it has gravity like Earth, and you see like the pipes come shooting out and immediately crash down to the comet. And sometimes there's like very low gravity and people are bouncing around. And so it was very inconsistent with the orbital mechanic, well, with the gravitational mechanics at least. Though they did use a slingshot maneuver, so that was pretty cool. I love Star Wars too, but the orbital mechanics is very brushed over in in the series of movies, but it's still a great and enjoyable show. I'm not a big fan of the new ones compared to the old ones, but they're still decent. Okay, we got rocket launch videos seem to depict that space vehicle spinning as it goes up. What is the reason for this spin? So this is a great question as well. So if we have any more prizes, we can give one for that. It's called spin stabilization, and you'll see some rockets use this. So what happens is, instead of having fins or a vectoring engine, which would add some mass to your rocket, what generally will happen is you spin the rocket, kind of like how a football travels through the air. If you've ever seen American football where they chuck the ball, they don't just chuck it, same with rugby. You don't just throw the ball, you spin it to the other person. It stabilizes it in flight so it'll stay on its trajectory. Exactly. It's just like rifling in a bullet. If you ever seen a barrel of a rifle, it's got like this corkscrew that travels through it, and that causes the bullet to spin while it's in the chamber so that it stays stable along its flight path. Called spin stabilization. My pleasure. Can a group of friends, students, ordinary people put a camera in orbit or crash something onto the moon and send back pictures? So it depends on how much finances you're willing to put towards this project. Getting something into space or near space, people have done that with weather balloons. So those are generally filled with hydrogen or helium. As you can imagine, helium's a little bit more favored, even though it doesn't go as high because it doesn't tend to explode. And you can get quite close to space with those. I don't know if you can get above the Kármán line with that, but maybe if you had like a model rocket attached to a series of weather balloons, you could get quite high up, then fly the model rocket up into space. But to get to orbit would be very cost prohibitive, though there are quite a few startup rocket companies. There's one in New Zealand. I forget its name now. They're a startup venture capital funding, and they're trying to launch small payloads into orbit with some good success as well, actually. So yeah, it's all
Rocket
dependent
Lab, I
on
think.
Rocket Lab. That's them. As far as crashing something on the moon, there's probably some sort of international law against doing that without prior authorization. I know that for the Apollo landings, what they actually did is the translunar injection stage of the rocket. That's the bit that uses the thrust to get the command module and the lunar module on a course to go to the moon. That was actually set up so that it would impact the moon a little bit later. And that was so that they could set up seismometers to figure out the different properties of the moon, like was it hollow, that sort of thing. So this big fuel tank expended with and a few engines would crash into it, and they would measure the seismic activity from that crash. So it has been done before. All right, I think that's all the questions. Yeah, good to see you too, Andre. Even if I didn't see your face. Good to see you in the chat. And thanks everybody for joining. It's been great.
Yeah.
If you have any burning questions at 3 a.m., just drop me a message on Twitter, and I'll see if I can get to that.
Cool. Thank you so much, Brian.
My pleasure.
That was fantastic. A lot of information and a lot of work gone into that presentation. So, and I know that you think about it a lot. So it's quite good to get it out on something.
Yeah, this is great.
Brilliant stuff. Yeah. So, guys, if everyone's listening, if you're interested in these kind of things that are not completely software but still kind of engineering and interesting, just let us know, and maybe we can organize more of these kind of talks as well. Where it's not strictly like
Kubernetes.
learning about Kubernetes and Agile. So it's just a bit more interesting stuff, and where software can go, because obviously these things don't fly with a pilot at all. It's all controlled by software, so it's pretty interesting stuff.
That's a good point. I don't know if you've ever seen a picture of like the inside of the space shuttle cockpit, and there's just dials and buttons and knobs and all sorts of things around. And if you look at how the Falcon 9 crew capsule looks, it's got 3 touchscreen TVs, if I'm not mistaken, and everything's done.
Yeah, and that's only just for cats and Netflix and
Twitter. Basically, it's an entertainment station. So don't trust the astronauts to do anything.
Yeah, they're going to keep them distracted from breaking the station.
Yeah,
that's actually an interesting one. Do you know what systems they're running there? I mean, is it just like a Linux thing, or is it their own OS? I mean,
I can't imagine they wrote their own OS. They like, if anything, they would have used some sort of Linux distro to customize it. If I remember right, I remember that the space suits were running Node.js software. This was not SpaceX. This is NASA spacesuits. They were running some Node applications. I could be wrong about that. I imagine they're using Linux. I can't imagine that they're using Windows on SpaceX. But mind you, with the styling, maybe it's Mac OS under the hood.
What did the space shuttle use? It must have been custom, just like some very 8-bit stuff or 16-bit thing going on.
Yeah, probably designed with formal programming where every piece of code was mapped out with, there's diagrams and stuff first.
Yeah.
I've seen pictures from the ISS of Windows machines doing stuff. So, yeah.
Yeah, I'm sure just the general computers they have up there is Windows or something. Yeah, it'll be interesting to figure out what they're actually running, and in Blue Origin as well, what's going on there.
Yeah, I did look into it, and you can't actually write software for rocket engines if you're not a naturalized American citizen. So you have to go through a naturalization process because it's considered weapons technology, which is sad.
Do you think that would still apply, for like you mentioned, there's other startups like Rocket Lab as well, which is half New Zealand, half
I can't imagine the New Zealanders have that requirement. So I think you'd be fine there.
Yeah.
Let's go to New Zealand, Bradley.
And yes, New Zealand.
Crikey.
You want a chip, bro? Okay, cool stuff. I think yeah, let's call it. But thanks a million, Ryan. It was really interesting, and I'm sure we could do like 10 more of these. But thanks everyone for joining, and thanks for everyone that stayed to listen to extra questions and that. And yeah, if you got anything more, just ping Ryan on Twitter or ZA Tech Slack, and I'm sure he'll get back to you.
Yeah, my
Or
pleasure.
at
Thanks for
Elon
having
Musk.
me.
Cool. Cheers, guys.
Cheers.
Cheers, Ryan. Thanks very much. Cheers.